You may recall from the addition section previously, we had different properties, number properties, things that are different ways our numbers behave when you do certain operations to them. We're going to explore those again for multiplication, and we also have one additional one. So we may go through these a little faster because we've already seen these. We're just going to see how they now relate to multiplication. So the first one is the closure property for multiplication, which states for any whole numbers, again, these are whole numbers, for any whole numbers A and B, A times B is a unique whole number. Again, closure means that when you're working with a specific set, meaning whole numbers, and you perform the operation of multiplication, your result, your product is also going to be a whole number. So for multiplication, closure of whole numbers is something that is true. Pick any two whole numbers. 3 times 4 is equal to 12. 1 times 73 is equal to 73. Even 0. 0 times 5 is equal to 0. The answer, the product, right? All of our products here are also whole numbers, right? That's what it means for you to have closure with that particular operation and that particular set of numbers. The second one we'll look at also should look familiar, and it is called the identity property. Identity property. And remember, with addition and identity, it was all about what can you do, what can you add to get the same number back? Remember, identity is who you really are. With multiplication, well, actually, with addition, it was 0. When you add 0, you get the same number back. But with multiplication, the identity is the number 1. The number 1 is called the identity for multiplication. Because when you multiply by 1, you get the same number. It leaves the identity of the number unchanged. 1 times 14 equals 14. 1 times 0 equals 0. 1 times 73,459 is equal to 73,459. For any whole number B, 1 times B is the same thing as B times 1, which is just B. 1 is the unique identity for multiplication. All right. So there's 2 of our number properties, closure and the identity property. The next one we will do is the commutative property for multiplication. So the commutative property, actually see, before I even put it up there, maybe pause and see if you can remember what the commutative property was for addition. And so the commutative property for multiplication is very similar. It looks like this. Remember, I always relate commuting to driving to work and then driving home. You go in one direction and then you turn around and you drive the other direction. Multiplication works the same way. For any whole numbers A and B, A times B is equal to B times A. They give you the same answer, the same product. 3 times 4 is equal to 12. Flip them around. 4 times 3 is also equal to 12. Now, I'm going to show you a couple other aspects of the commutative property that do matter, that are important to recognize. Let's think about 7 times 5. Imagine this multiplication problem. You could imagine an array. Picture the array for 7 times 5. Remember the rectangular representation. Notice how you can arrange it 2 different ways. You can look at it as this, where you have groups of 5 and you have 7 of them, right? This represents 7 times 5. Or you can flip it around. Just imagine rotating it 90 degrees. And now it's 5 groups of 7. It's still the same number of individual units, either way. But showing it like that and demonstrating it using the rectangles can sometimes be helpful. Another thing that does matter, and that the commutative property helps with, is this particular content standard from the Common Core. And it says, by the end of grade 3, students should know from memory all products of two one-digit numbers. So every student should automatically know that 3 times 7 is equal to 21, 5 times 6 is equal to 30, 9 times 9 is equal to 81, etc. They should know all of those things, right? And I will say that that is one of the of all the things we do, right? Maybe when students don't know that, it presents so many later challenges. And so all the things that we are doing, all the things that you are learning about in this class so far are meant to help students understand all of the underlying mathematical ideas that help them grasp these concepts. Because if you don't recognize that the number 3 is just represented by that many dots, right? Instantly sort of know that, and that 7 is 7 of them. 1, 2, 3, 4, 5, 6, 7. Just instantly connecting those ideas. Then even knowing that 7 times 3 is 21 can be a difficult concept, because as we just saw, a rectangular array for 7 times 3 might look something like this, right? Where you've got all of those individual little squares or dots, right? 7 times 3 is that. And connecting this collection of symbols to this concept is what allows students to, quote, memorize 3 times 7 equals 21, okay? If they don't have that, you're just sort of memorizing groups of symbols, and that's where it becomes hard. This has to be the underlying concept behind 3 times 7 and 7 times 3. So why am I talking about this in terms of the commutative property? Maybe you already know. We discussed this back in the addition section. There's all the groups of single-digit numbers times the other single-digit numbers. And what I've got circled here is 7 times 3 is 21, but also 3 times 7 is 21. And so if you understand that commutative property really well, half of your grid is already taken care of, right? You don't have to necessarily memorize or understand all of those. You just need to know half of them. As long as you know 3 times 7, then you also know 7 times 3, right? And so that commutative property is essential for helping students understand that they only really need to know some of those, okay? The next property that also will look familiar to you is the associative property. And just like before, what I want you to do is see if you can remember what the associative property looked like for addition, and then maybe even take a guess at what the associative property for multiplication is. Pause that video and see if you can do that. If you did that, what you probably came up with was an idea that looked like this. The associative property for multiplication says that for any whole numbers a, b, and c, a times, where a is outside, the product of b times c is equal to the product of a times b, and then group together times c. Remember, associate. Who do you want to be with? Who do you want to be next to? Who does b, which is in the middle, want to associate with? Does it want to associate with c, or does it want to associate with a? It doesn't matter. You're going to get the same answer either way. So again, if we look at 6 times 7 times 4, if we have to do that multiplication, we can choose to do 7 times 4 first, which would be 28, or we can group them, list them in the same order, but group 6 times 7 to be 42 first, and then times 4. It doesn't matter. I look at that and I think that's easier to do in my head to get 168 than it is this one. But they do both equal 168. So let's examine the associative property a little bit more. What I'm going to do is examine this this particular problem, which is 5 times 3 times 4. Okay, so we're going to look at that multiplication problem. And the first thing we're going to do is look at it. We're going to group it one way, and then we're going to group it the other way. And so the first way is where we're going to have, let's see, groups that look like this. Take a second and just examine that picture and notice how it relates to the problem at hand. And now take a look at this picture and observe how it relates to the problem at hand. So what do we notice here? In this first example, what we have is 3 up and down, and then we have 4 here. So this is showing 3 times 4. And then it's showing how many groups of those? 1, 2, 3, 4, 5. So in this arrangement, in this array, we have 3 times 4, 3 times 4, 3 times 4, 3 times 4, and 3 times 4, 5 times. And so each individual rectangle has 12. There's 12 there, there's 12 here, there's 12 here, here, and here. And that's what this gives us. And then we take 5 groups of that. 5 groups of 12 is equal to a total of 60. We can look at the same problem as 3 rows of 5 columns. 3 times 5 is 15, 15 here, 15 here, and 15 here. That's this multiplication. And we have 4 groups of them, 1, 2, 3, and 4. 15 times 4 is also equal to 60. It's the same number of individual units. It's just grouped a little differently, right? And so those different arrays can help us see the different arrangements. Do we want to group the 5 and 3 together, or would we rather group the 3 and the 4 together? It's going to be the same in either case. So in this one, what we're going to do is we're going to play with a particular multiplication problem, 25 times 46 times 4. And the previous 2 properties we've examined were the associative and the commutative. In this case, we're going to utilize both of those. And I want to see if you can look at those, apply both the commutative property and the associative property to make this problem quite easy to do, or somewhat easy to do mentally. All right? So go ahead and pause the video and try that one. So what you might have done, or what you might have noticed, is that I gave you some nice numbers to work with, but they're not next to each other. You might have noticed right away that there's a 25 and a 4. And 25 times 4 is equal to 100. That's a nice, easy number to work with. So maybe the first thing you do is you commute these 2 numbers, meaning you change their order. And you say this can be stated as 25 times 4 times 46, rearranging things. Then you want to group the 25 and the 4, meaning you're going to associate the 25 and the 4. That product is 100. And then when we multiply 100 times 46, we end up with 4,600. Remember that idea we talked about earlier in another video, multiplying by 10 shifts the 4 and the 6 over one spot. If we multiply by 100, it's really shifting them over 2 spots. So we end up with 2 other zeros, 4,600. So what you can see there is we can utilize commutative properties, associative properties to make our problems a little easier to do. The last property we will talk about in this video is the distributive property. That might be one you're familiar with. And if you are, see if you maybe even pause and say, ooh, can I remember what the distributive property looks like? You may have, if you did that, you may have come up with something that looked like this. That type of problem might look familiar. And so the official name for a problem that looks like this is the distributive property for multiplication over addition. And here's our formal definition for it. Take a minute, pause the video, read this, and just try to make sense of this one, because this is a new property for us. One thing you might notice when you examine this property is that what we have here is a multiplication problem and an addition problem. And it's called multiplication over addition. And I'll explain that why that is in a minute. When you examine this, we've got our equal sign in the middle, which means this thing over here is going to become this thing when we do distribution. And so we start with the A, and notice over here, we only see one A on the left, but once we distribute, we actually see two A's. And instead of having one multiplication, we have two multiplications. It's often called multiplication over addition because we are multiplying the A times both of the numbers being added. It's A times B here and A times C here. The addition then follows between those two products. And when you have numbers like 2, 3, and 4, you can really choose to do the problem a couple different ways. You could choose to add the numbers on the inside first and do 2 times 7, or you could do this distribution where you distribute the 2 and say it's 2 times 3, and then you're going to add that to the 2 times 4. And what you arrive at is 6 plus 8. When you do both of those multiplications, 6 plus 8 is 14, which is the same thing you would get if you multiplied 2 times 7. And so this can also be a really, really useful tool when we start to play around with different numbers and try to do multiplication in different ways. And so what I'm going to show you is one example of that. And we're going to look at this later in the next video as well. So let's say we want to do the product 6 times 7. 6 times 7. And maybe you have young learners who those are big numbers for, right? Maybe they might know some of their smaller products back on that multiplication grid, but they don't know what 6 times 7 is yet. So to help them make sense of it, we can cut our array up into two different groups. And so you might draw something that looks like this. Let's explore this for a moment. This array, if you just draw a 6 by 7 array, which is hard to do on this grid, but it would look something like this, right? 6 by 7. We would have 7 columns and 6 rows, right? So this would be a 6 by 7 grid. And we could count all of those, obviously, and come up with 42. Or we could break our 7 up into some smaller numbers, where you see we have a 6 by 3 miniature array and a 6 by 4 miniature array here. And we can separate those things. So your younger learners might know that 6 times 3 is 18, and they might know that 6 times 4 is 24. And then when we group those, 24 plus 18 is equal to 42. So 6 times 7, this entire array, has a collection of 42 blocks. So this can be demonstrated as that distributive property. Instead of doing 6 times 7, what you can do is 6 times some addition problem that equals 7, like 3 plus 4. 6 times 3 is 18. 6 times 4 is 24, and we can add those to get 42. And so often the distributive property is something that you might do as a way to solve a more complex problem. And it is one of the things we will look at in the next video when we start to examine ways to do multiplication calculations mentally.